That's right. So thank you so much. And indeed, it's an honor to be here. And it's a double honor to be here as the last speaker of this thematic program, because I was pretty sure that they will not let me in. Apparently, I couldn't come last week because of my teaching duties. And then, but then Adrian Constantin and you, the organizers, and Nathan Pardor, thanks him very much, wrote me back that even though I can't attend the workshop, but I still can have this presentation here. And of course, it's indeed a tremendous honor, as always, to be here at the Schrödinger Institute. And because of this particularly interesting situation that I had absolutely no idea what kind of people will actually show up 1 week after the workshop for this talk, I decided to make it a more general introduction to what we are doing. And indeed, we have this laboratory called von Kármán. Theodor von Kármán was actually born in Budapest. So this is one of the reasons why we named our laboratory after him, which is, to the best of our knowledge, is at least in kind of its I would say, roughly 600 kilometer radius. This is the only laboratory that was funded especially to model environmental hydrodynamics or geophysical fluid dynamics. And yeah, that's where I'm working. I'm currently the head of this lab. And let's see what we're doing here. Now we are trying to do experiments. Now, of course, experiment is a sole judge of scientific truth, but of course, with systems like climate or atmospheric circulation, it's not really easy to conduct experiments. And this is one of the reasons why it's very hard to disentangle all these interconnected processes, various feedbacks, and many complex mechanisms that interplay and make climate system as complicated as we know it. So the idea is to make a kind of minimalistic model that is as simple as possible, but no simpler than that. And it's known since the 1950s, I guess, that you can actually make a laboratory experiment or a laboratory experimental configuration that enables the experimenter to analyze the basic underlying dynamics of the atmospheric circulation, including baroclinic instability, Rossby waves, and surprisingly many phenomena like spreading of tracers, for example, and stuff like that. It turns out that even though, of course, atmosphere is a very complex thing, but if you have a rotating tank with the differential heating, that means heating on one side and cooling on the other side, and you set the non-dimensional numbers correctly, you can have a pretty much a weather-like dynamics. And this is precisely what we're doing. So this minimal model looks like that, a physicist's point of view of what is happening in the Earth's atmosphere. You have a differentially heated domain, this warm in the equator, so you can imagine it as a vertical wall around the equator. And here in the polar regions, you have a cooling wall. Of course, this is kind of a representation of the differential incoming solar flux. And then we have the rotation. And the idea is that if we have these two, then we can make a laboratory experiment. Which is essentially a flat Earth model of the Northern Hemisphere. So if you compare this sketch of this experimental setup with this other sketch, then you can see that precisely what is happening here is that we say that we have a cylindrical cooling in the center that represents the Arctic, and then we have the equator, or so subtropics, so to say, rather. And this is basically the outer side wall, the outer rim of the cylindrical domain. And yes, as you can see, we have several experiments. One is in Budapest, one other in Cottbus, that is in Germany, where my close collaborators work, and they too have a laboratory there with this so-called rotating annulus. And of course, we have to say that it was introduced by the groups of Fultz and Hyde back in the 1950s, maybe even late 40s. The first publications about this setting is from the 1950s, for sure. So the setup in Cottbus is a rotating cylinder filled up with water up to a certain height, and then of course it's also rotating. So these are the geometrical dimensions. Oops, sorry for that. For Cottbus, and this is how it actually looks like in reality. And this is the one with all these wires. This is the one in Budapest. And yes, this is the biggest one on the planet of this kind, which is located in Tallahassee, at the Florida State University in the basement. And yes, I've been there too last summer to do some experiments with this. And the reason why they have different sizes is, as we will see, is that with different size setups, you can reach different kind of states of flow patterns in this. Yeah, absolutely. Yeah, that's right. So for those who are listening in online, the question is whether we are trying to model the beta effect in this particular setup. And the answer is no, in this setup, we cannot really do that. I mean, there is this widely used demonstration setup for the beta effect, which has the sloping bottom, a conical bottom, right? And then you can actually use it to model kind of non-thermally driven Rossby waves. So instead of the beta effect, you will have to change the potential vorticity there, you have a different depth. But in these setups, the bottom is actually flat. So we are not modeling the beta effect at all. And this is exactly why it's very interesting. So that's why I said it's a flat Earth model, because it's also a flat Earth model in the sense that even the first approximation of the curvature is not included in this model, but still, as it is basically, I would say that the general consensus in this community is that indeed a lot of things can be modeled. And this is the surprising thing, actually, that even though we are missing a lot of essential components like the beta effect, but still Rossby wave dynamics can be observed. Yeah, so yeah, these are the tanks. All of them have a flat bottom. And okay, what is happening here is that we have a heating on one side and cooling on the other side. So the water rises on the heating side and goes down on the cooling side. So they will be connected by this. They kind of form a convective cell, but this is a sideways convective cell. So it's important because unlike in the traditional Rayleigh-Bénard kind of setting, here both the heating and cooling are happening at the same height. Therefore, you don't have to fight gravity, which practically means that there is no such a thing technically as a critical Rayleigh number. So however small temperature difference you have an overturning flow in this setup. And yeah, it's supposed to be an animation, but this is now a PDF. So now if it wasn't an animation, you could actually see a video of tracer particles rising and going around from a PIV, particle image velocimetry video that we took in our laboratory. But so this is how this overturning would look like without rotation. So it would be kind of boring in a sense, but then we turn on rotation. And of course, then things will become much more interesting, most notably because we will have the baroclinic instability. Now, it turns out that if you rotate the setup and you have this differential heating and cooling, which kind of creates a density gradient, but then, of course, without the rotation, the density interfaces in an equilibrium configuration should be horizontal. But in a rotating system, and we will have these tilted isotherms, which will be balanced by the thermal wind, which in this case would come out of the plane of the board. And because of this kind of geostrophic balance, these tilted isotherms actually are stable, but if we have a flow that is kind of follows the boundary here, for example, the bottom boundary, and goes horizontally, it also means that this particle, if it keeps its density, and it does practically on these time scales, so this water parcel that moves here will get to a domain where the environment has a higher density, so it will rise. So this is an instability, because a smaller perturbation of the position will actually yield a larger displacement. So therefore, kind of, we can say that a sort of a potential energy is kind of pumped here into this domain, and this will released, in a sense, to form wave patterns like that. And of course, there is a pretty good theory for that. But now, instead of showing that in details, now let's see what is actually happening from the experimentalist point of view. If you look at this laboratory tank with an infrared camera that is co-rotating with the setup and is mounted above. And the infrared, the penetration depth of this infrared wavelength domain into water is actually like on the order of millimeters, okay? So really what we see in these images is just surface temperature, skin temperature. And A, B, C, and D, in this order, we keep the temperature constant between this cooled internal domain and the heated external rim, but we increase omega, that is the angular frequency of rotation. And indeed, what we see is that we see more and more larger and larger wave numbers. So in the case A, when the setting is not rotating or rotating very slowly, then we don't see anything at all. Yeah, as kind of expected. But then when we increase the rotation rate, we see kind of we can already call this Rossby wave, the Rossby wave of wave number 2, 3, 4, and so on and so forth. And then when these eddies become smaller and smaller, that means that they have more space to move freely, because here you can see that these eddies are kind of tightly pegged. So the maximum number of eddies that can fit here into this angular gap is basically determined by the size of the gap and the Rossby radius. That has to do obviously with the rotation rate. But if you increase the rotation faster, you get smaller and smaller eddies, which get, after a while, they get much smaller than these gap widths, which means that they can eventually freely propagate, and then we will no longer have these regular patterns, but instead we arrive to the geostrophic or quasi-geostrophic turbulence, which is a really weather-like situation. Yeah. Yeah, it is a free surface on the top. And we have a continuous stratification of temperature. Yeah, that's right. So otherwise, if it's important actually, even from the observational point of view, it's important to have a free surface, because as I said, we are observing it in the infrared camera. And if you had, for example, an acrylic or something covering on it, then you would not see anything with this technique, at least. Yeah, so indeed, it's free surface, but it's important to emphasize that the laboratory tank actually itself is actually way taller than the water level, right? Because otherwise someone may ask whether wind shear in the lab or like shear with the air, which is not co-rotating, would modify the flow. But what we can say is that we checked it actually, and it turns out that this is not really an effect as long as the tank is much higher than the water level. So yeah, indeed. So if yes. Right. Yeah, we can check it and we will get to that point. However, it's important to note that there are multiple equilibria in this system, which are, and even the theory for that is not really clear. So what we can see is that the wave number that you observe actually depends also on the history. So if you come to the same omega, same rotation rate from below with the spin-up initiations, even if you do slowly, but you may converge to one state, let's say a wave number 3, and it may well happen then if you start from a fast rotating configuration and slowly decrease the rotation rate, and you arrive at the same time, you get to another solution of wave number 4. And so there is a high hysteresis, obviously, which makes it very interesting. Yeah, but not everywhere. So it's just yeah. So for example, the boundary between the onset of this baroclinic instability, so between this axially symmetric configuration and something else, that boundary is actually very very solid. So even this is very kind of fixed, independent of the initiation procedure, for example. Now, okay, so what we can see here is that the slow rotating case is kind of similar to the atmosphere of Venus in the sense that Venus is a very slow rotator. I think one day on Venus lasts for 243 Earth days, which makes it really a very slow rotating planet. And therefore, obviously, as we can see in this spacecraft imagery, the flow patterns in the Venus atmosphere, Venusian atmosphere, are really axially symmetrical. However, for example, in the case of Earth, it's more like that. We can see this meandering jet between the cold polar vortex and this kind of mid-latitudes. And really, in the case of Earth, of course, it's already a kind of an irregular pattern. The atmosphere of Mars, however, is in the same range in terms of the parameters of hydrodynamic stability as this, for example, this wave number 3 or 4 configuration, but I don't know precisely the wave number for Mars. And of course, it also depends on the seasons, but the Martian atmosphere is usually kind of used as an example for a regular baroclinic wave or Rossby wave like these, which is not that irregular as the ones on Earth. But let's see what determines these. Now, from the non-dimensionalization of the rotating Navier-Stokes equations, we figure out that indeed the two most relevant parameters for this kind of instability are the Taylor and the thermal Rossby numbers. The Taylor number is basically the ratio of the Coriolis effect and the viscous acceleration, whereas Rossby number has to do with pretty much the time scale that the flow takes to cross the domain, which has a characteristic size L, which is in this case B minus A, which is the gap width in this particular case. So the distance between the inner and the outer cylinder. But if you calculate this number for a planet, then you can easily put just the radius of the planet here. And omega is the rotation rate. Delta T, of course, is the temperature difference between so to say the equator and the pole. Alpha is the volumetric thermal expansion coefficient. D is the thickness of the layer, and G is the gravitational acceleration. And the Taylor number has the same geometrical parameters and the kinematic viscosity here, of course. And we can see that this is basically the regime diagram. And kind of the ED model pretty much predicts this outer edge of this anvil-shaped domain, but of course not everything. Basically, we can say that if you look at it, these are logarithmic scales of Taylor and Rossby, and Taylor number doesn't have the delta T in it, but it has omega square. Rossby numbers has omega square in the denominator and as delta T here, up here, which means that practically a constant delta T line would be a -1 slope here. And indeed, I happen to say that there is no such a thing as a critical Rayleigh number, but in reality, because of the viscous drag, there is such a small temperature difference where actually this overturning flow is damped by the viscous drag. So that's why pretty much this is the reason why this domain, this bottom domain, stays axially symmetrical, even though the Rossby numbers are small. Now, generally, of course, a small Rossby number would mean a geostrophical turbulence. Yeah, but however, if the Taylor number is large enough, which means that we can easily overcome the viscous drag, then at small Rossby numbers, we have this kind of Earth weather-like irregularity, which is practically geostrophic turbulence. And now our idea was that, we can investigate for example, the temperature signals in a setup like that, and see how the statistical properties of these extreme events actually scale with the Rossby number. Now, why the Rossby number? Well, Rossby number, as we could see, scales with delta T, the temperature difference, so to say, between the equator and the pole. And of course, we know that with the ongoing climate change, we have this polar amplification, which means that the delta T in reality has a decreasing trend. And of course, in the meantime, we keep hearing these news that weather is becoming more extreme. Okay, it's hard to define what this actually means, but yeah, one may have the idea that it would be interesting to see how the decreasing delta T affects the temperature signals in a minimalistic model of the meridional atmospheric circulation as this one. So this is precisely what we did. And to get to the small Rossby numbers, if you go back to this geometry, you see that if you want to have a small enough Rossby number, you can do it several ways. You can have it with a small delta T, but then you're here in this regime. You can have a small delta, a small d, small thickness, but then a lot of other effects like bottom shear and things like that come to play. So basically, the reason to get to a smaller delta T, of course, you can still increase omega, but besides, it's also good if you have a large horizontal scale, B minus A. So that's precisely the reason why we went to Tallahassee, where we have this large 3-meter wide version of this setting that we have in smaller here. And BTU is a Brandenburg Technical University in Cottbus, Germany, where we had this other setting. And these are practically what we measured. Were just pointwise temperature time series from this laboratory tank. And then we could see how the temperature flew in a quasi-equilibrium state. And we were running experiments with different delta T's, so different Rossby numbers. We didn't change the rotation rate or the geometrical parameters like water depth and stuff like that. We didn't change that within a series of experiments. And so basically the only control parameter that we varied within a series of runs was the delta T, just to imitate this, how they call it, polar amplification. That's how they call it. So this thing that the delta T is actually, the meridional temperature difference is decreasing. Now, the interesting thing is that if you see basically the same histograms of temperature fluctuations from this sensor. And both panels show exactly the same, but here the ones from the Tallahassee instrument is highlighted with coloring. Coloring is based on the logarithm of the Rossby number. And in the other panel, the ones that are highlighted with the same coloring are the experiments from Cottbus. But in both cases, you can actually see that, yeah, indeed, as one may expect, with an increasing delta T, you will have an increasing and less Gaussian kind of distribution. And if you just take the quantiles of this story, so like, for example, the 5 percentile, 95 percentile, for example, and stuff like that, you can nicely see this widening. And these are the data points from, this is practically the temperature fluctuation versus the Rossby number. And you can see that indeed this range of temperature fluctuations becomes larger. And it is not a trivial thing. So one may think that, yeah, of course, a Rossby number is known to be a non-dimensional temperature scale parameter. Yeah, this is true. But what is very interesting is that it appears from this diagram is that there's a really perfect match. So again, for example, these orange points are from the Cottbus experiment, which is this small, and the red points are from the Tallahassee experiment, which is 3 meters wide. But we know that Rossby number is not the only relevant parameter. So if we get back to here, I tell you that for example, the Taylor number, which we didn't vary, as I said, because we only think that we changed within a series of experiments was the delta T. So within a sequence of experiments in Cottbus and in Tallahassee, we didn't actually change the Taylor number at all. But Taylor number for one experiment is like 10 to the 8th. That's the one for Cottbus. And it's 10 to the 12th, which is not even on this scale, for the Tallahassee runs. Which means that the Taylor numbers are vastly different, orders of magnitudes different, but still it appears that this scaling is not influenced by the Taylor number, which is something kind of non-trivial, I would say. And this data collapse was also remarkably good. So with saying that it should also depend on the Taylor number, but apparently it only depends on the Rossby number, and it yields a beautiful data collapse. So that was kind of a surprise for me. Yeah. Of course, anyway, even at the Taylor number of 10 to the 8th, you can say that it's a minor rho, right? Because 10 to the 8th is like huge, which means the viscosity effect is kind of almost negligible, but still it's interesting to see that even if the two experiments in terms of the Taylor number are 4 orders of magnitude apart, and yet you still see a perfect match of perfect data collapse with the Rossby number only. So it means, and of course it's important to emphasize that even in the atmospheric domain, it's in the same regime, right? So the Taylor, if you calculate the Taylor number for the North Hemisphere atmosphere, you get again something like 10 to the 12th, I guess. So which means that this is precisely the same order of magnitude as the one for the Tallahassee run. And it's good to know that, for example, if it was only the Rossby wave dynamics, then what we would expect is that we have a decreasing delta T, decreasing thermal Rossby number in the actual Earth system. So what we would expect is to get narrower distributions. And of course, the Earth system is way more complex than that. But now we can say that, okay, so if you see that the opposite is happening, you cannot really blame on the Rossby wave dynamics. And I encountered this several times, that in several papers, it's blamed on the Rossby waves. It's because of the more meandering Rossby waves that the temperature distributions widen, and there will be more extreme cold and more extreme warm inbreaks or whatever, or outbreaks and cold outbreaks or whatever they is called, or heat waves, because the Rossby waves are more meandering. But now we see that as it's not that, it's an oversimplification of what is happening, and this is. And another thing is that the time scale, that's interesting also, that if we increase the temperature and we look at the spectrum of these temperature fluctuation time series, we can see that there's, in all cases, we can see that as they should be, they are kind of a red noise-like system with a decreasing spectrum up to a certain point. And above that point, there is this more like a gray or whatever, a white noise-like part. So correlated and the less correlated domain in the spectrum. And there is a relatively clear cutoff or kink where this kind of like red noise-like behavior ends, and then it's more like uncorrelated noise above a certain frequency scale. And we can see that in both experiments also, that this is also shifting with the delta T. So this, if we kind of, with like linear regressions, we kind of try to figure out where this F star or F asterisk is, which we can associate with this kink. Then we can see again that if we have a decreasing delta T, you have a higher cutoff frequency, which means that indeed, if the delta T is larger, then more time scales can be considered correlated, because the domain of correlated time scales kind of widens in the frequency domain. And actually the same holds for the other end of the domain, for the analysis of which we we also conducted, which is a kind of has to do with the so-called persistence. So persistence, what the meteorologists love to use, has to do with the slope and this other kind of kink which we have here. And we also conducted this analysis using the trended fluctuation analysis, and both actually come gives us the same message, that apparently with increasing delta T, actually the weather is becoming also more persistent, kind of more, if you wish, more predictable in the sense, with larger delta T. So that's interesting. So even though with decreasing delta T that we are having in the atmosphere, in decreasing delta T, we would expect that the fluctuations in magnitude, of course, will be smaller, but also the fluctuations will be less predictable in a sense. So, okay, another thing is that we were also analyzing the extremes of the temperature jumps. So we kind of took the temperature fluctuation signal and took their derivatives and look at the extreme jumps, so extreme large derivatives. Of course, we had to smooth them because, of course, the numerical derivation is very sensitive to noise and so on and so forth. But really, the interesting thing was that here we found another scaling that is also interesting, but kind of explainable. Obviously, here time comes into play. So the Rossby number, which is not a time scale, but rather a non-dimensional temperature scale, will not be the good scale parameter. However, the temperature jumps appear to scale with this combination of parameters. Or something that is proportional to this combination of parameters, which is the delta T squared divided by the horizontal scale and the omega, the angular frequency. And then, yeah, kind of it's understandable why, because if we assume that the Lagrangian, we consider that the fluid tracers or fluid parcels that don't really change their density, which of Boussinesq approximation, so to say, then the hydrodynamical derivative must vanish for temperature. So this delta T would be proportional to this combination of gradient T times U, where the U velocity scale can be also approximated from the delta T temperature difference and the Rossby number and so on. So we can easily get to this kind of order of magnitude estimate for the temperature derivatives. And indeed, it turns out that it kind of follows something like that, but it's not really the important message. Really, what is more important to me is that indeed, there's a narrower temperature distribution would be something in this model that we would observe for a polar amplification scenario. And yes, indeed, that this persistence scales with this 1 over delta T. That's also, to me, that is interesting. And again, if we are not claiming here that we kind of solved anything that has to do with the actual climate system, but instead we are going the other way around. We say that if it was really due to the Rossby waves, as many oversimplification, many explanations kind of claim, then we say that it's not really that easy. However, we can also use the same model for a minimalistic model of the ocean circulation as well. But of course, in the case of the ocean, there is practically just one place on Earth where you can have this kind of boundary condition without the continents getting in the way, and this is the Southern Ocean, of course. So for Southern Ocean, of course, is baroclinic unstable. But of course, here the big current is the ACC, which is Antarctic circumpolar current, which is basically wind-driven, but not entirely, but mostly. But again, the interesting idea was here whether this kind of dynamics of the ACC can also be modeled in this setup. But really, what motivated us here was really this paleoclimatic event, namely the opening of the Drake Passage and the Tasmanian Seaway that happened 34 million years ago, which is the eocene-oligocene transition. And again, what we can read in the textbooks is that the Drake Passage opened up, and therefore the Antarctic circumpolar current could form, and therefore basically the Antarctica was kind of separated or isolated, and that's why the glaciation of Antarctica started. Because it's interesting that even though Antarctica was in the very same position already back in the Cretaceous period, but still this permanent ice cover only formed on the Antarctica 34 million years ago. So really, it's an interesting question why it happened. And again, the traditional explanation is that the Drake Passage opened, and you had this formation of ACC, and therefore Antarctica was kind of isolated, and that's the reason why there is a white Antarctica nowadays. However, this is also challenged by some other commentaries, like, for example, this Decanto and Pollard paper that says that it was more of a consequence of a decreasing CO2 level in the atmosphere, and that was the primary reason for the glaciation of Antarctica. Now, what we did was a very oversimplified model again, that we divided this baroclinic wave tank with a removable barrier, and to see how the temperature distributions change if you open up this barrier. So you get from a closed, so to say, a closed Drake Passage configuration to an open Drake Passage configuration, and to see what happens. And really, the most important observation was this, that in the tank, the mean surface temperature kind of increased when we removed the barrier in all the experiments that we conducted. And of course, again, the same reasoning. We are not saying here that this is the model of the opening of the Drake Passage, but instead what we say is that in the textbook story that it opened up, and then suddenly the entire southern hemisphere got colder is kind of more tricky than that, because if it was just really this kind of dynamics, then it would actually be warmer. And really, this is what we observed in all the experiments. So this closed, open, it was always above. Now, from the fluid dynamics point of view, we kind of understand what happens here, of course, because when you open this up, open up the boundary, open the, so to say, the Drake Passage, then it means that you indeed initiate this ACC like thermal wind in the system, but this also inhibits the overturning. And if it inhibits the overturning, it means that the upper layer and the bottom layer will be more separated from each other. So there will be not much of a heat transfer between the top and the bottom layer in this configuration. And really what affects the climate is the top layer's temperature. So indeed, what we see in the laboratory kind of makes sense. You open this up, and then you have this overturning current, but this also means, this circumpolar current, but that also inhibits the overturning. So again, what you see on the surface, average temperature or mean surface temperature, it will not really be anymore a good proxy for the volumetric average of the temperature, not anymore. Before the opening, it was, because you had this overturning that ensured that there's an intensive thermal contact between the bottom layer and the top. So yeah, we kind of, this is what we've learned also from putting thermometers in the laboratory tank. So the top layer and the bottom layer, that indeed the two distributions were way more of temperature fluctuations were way more distinct when it was open. But really the question is why is it so much different from that in the actual paleoclimate time series, which obviously indicates that there was a cooling event. And of course, again, the reason for that is that the real atmosphere is, of course, more complex than that. And the most important thing which we could think of is the ice albedo feedback, which we apparently couldn't model in one of the many things that we couldn't model in this conceptual model. But we had friends with the GCM and the global climate model. And with this GCM, we managed to run simulations with a closed and an open passage. Unfortunately, in these plots, it is not visible, but this is actually, there was actually a built-in gap. We didn't actually model the paleo topography, but we did close the Drake Passage with the dam. And we could run both 4 types of simulations, open and closed Drake Passage, but also a simulation when we had the ice albedo feedback from the ocean on and off. So these are 4 types of simulations. And interestingly, between the open and closed configuration, there's not much of a difference in the temperature when the ice module, the ice albedo feedback was turned off, which means that indeed, this is what we found as a slightly higher temperature average for the open configuration in agreement with what we saw in the lab. But when we had the ice albedo feedback on, which means that if the temperature of a given parcel fell below a certain threshold, then it kind of painted it white, so it would affect the albedo feedback. Then if you had that, which obviously we couldn't model in the lab, then you get something that is consistent with the paleoclimate, which means that indeed there is a cooling, a global cooling in after the opening of the passage, but only if that module is turned on. So again, if the ice module is off, there is a slight global warming, but if the ice module is turned on, there is a marked global cooling. And then, okay, what is the message here? That is interesting because apparently it is not only, again, what is written in the textbooks that Drake Passage opened up in itself, it is not enough to explain what happened 34 million years ago. Because had it happened earlier, like in the beginning of the Eocene period, where there was so much CO2 in the atmosphere, then practically no water ice could have been stable at all. So there was no permanent snow anywhere on the planet, like 40 million years ago. Then what probably the same kind of a tectonic event, the opening of the passage, would have actually yielded a slight warming, which is interesting. So that this opening itself without the CO2 is not actually in itself enough to explain what happened. Okay, just one last thing, because we are getting close. Actually, I can hear from the and I can actually see that it's already 4. So so yeah, indeed, one other way to use this experiment is to model tidally logged exoplanets. This is something that we are trying to do now. Tidally logged exoplanets mean that vast majority of the so far discovered planets in other solar systems are such that they orbit their suns at such a small distance that they get into a tidally logged situation, which means that 1 year on these, for example, this is Proxima Centauri b, which is really the closest exoplanet in the just 4 light years away. And you can see this is the radial velocity time series. And you can see that they have and the period from this time series is actually the year, so the revolution period of the planet around its star. So it's like 10 days, and there are even shorter periods like that. So there are planets that kind of orbit their host stars in like 2 or 3 days, but they are tidally logged, which means just like the moon to Earth, which means in the case of planets is that they have a permanent day side and the permanent night side. But still, because they rotate so fast, or they orbit their star so fast, therefore they have a significant Coriolis effect. So, but they're very different boundary conditions. So we try to modify our laboratory experiment this way, and this is what we started to do. This is still rotating, of course, but with a very different boundary condition. In this case, the 1/2 of this external or this outer cylinder is heated and the other is cooled. And let's see what kind of flow patterns develop in this configuration. And we already started these experiments. But now, okay, I'm just running out of time, so I'm just showing you a few plots. So this is the regular. Or not regular, this is the usual, but of course already irregular geostrophic turbulent state. with a given Taylor and Rossby number for the classical configuration, but this is how it looks like for the exoplanet configuration. Apparently, there is a very different flow patterns, and I think it's a very interesting thing to learn what type of baroclinic instability can it develop in such a configuration, where basically the basic state is really the wave number 2, or wave number, or the dipole pattern. So even then, I think it will be very interesting. And again, and now for something completely different, we also have a laboratory model in which we try to understand the polar hexagon of Saturn, but this has nothing to do with baroclinic instability. Instead, it is a barotropic instability. And let me just skip a few slides because now I'm running out of time. But really, we have to say that really what is happening here is that these are differentially rotating planets, which means that the different latitudes, you have very different wind speeds. And so there is a shear that develops on it. And actually, this scale of this period, kind of this latitudinal distance between the subsequent wind domains is really determined by the Rhines scale. So it has to do really with the shape of the planet, that it is spherical. So in this case, actually, you can't ignore that, because all the reason why these stripes appear in Jupiter, but also on Saturn, just they are less visible, are really really a consequence of the Rhines scale. Peter Reed and others in 2009 did an experiment where they actually enforced a hexagonal flow in a rotating tank with a kind of a circular plexi surface that they also tried to pose a certain shear on the surface, and with that configuration they managed to have a wave number 6 pattern. But it would be nice, but otherwise it's hard to excite because of the lack of beta effect. And even in the configuration, they use the tilted bottom, but even then it turns out to be very hard to perform. So just let me skip a few slides about our experiments and finish with the future plan that we are doing. Is that now we are trying to do, or we proposed to the European Space Agency an experiment in which we have this rotating, differentially rotating boundary condition. Namely, in microgravity, you can have a free water surface, which is actually hemispherical. This is something that is not really possible to do on Earth. But then there, because of the surface tension, obviously you will have this large water drops. And the idea is just to because of the surface tension and adhesion forces, you can actually attach a kind of a hemispherical water droplet into a kind of platform. It's this big, like a tennis ball, so it's not a big thing, that rotates differentially. So it has a faster rotating equatorial domain, that is the blue, and this cap, this spherical cap, is the polar domain that rotates somewhat smaller to have this shear. And you can actually do this particle tracking in the water from video recordings that will be conducted by the astronauts. And this is something that we got positive scientific reviews already. So it already passed the European Space Agency's review procedure. So this is something that, of course, no one's for sure. This is a space program, so there are a lot of delays and budget overruns and stuff like that, as always. But the best case scenario is that this experiment will actually be performed sometimes during next year or the year after that. And yeah, and this is pretty much it, because anyway, we've run out of time, I presume. So let me summarize that basically the basic idea which I try to convey is that obviously with laboratory experiments, you cannot really model these kind of systems like Earth's atmosphere or planetary atmosphere, but certain aspects can be modeled, and in such a way you can actually test a lot of kind of ideas that people have in their minds. And and sometimes, as in the case of the Drake Passage opening, for example, or for the climate variability issue or this extreme weather events distribution kind of things, it kind of helps to guide the way people think about these problems, because apparently there are a lot of oversimplifications in the head of climate scientists, for example, about what can Rossby waves do and what they can't do. So that may be something. And also another reason that laboratory experiments even today actually make sense and are actually important is that they can really be used as analog computers. And what I mean is that a few years ago, in 2012, we had a program of the German Science Foundation that was called METSTRÖM, which means is an acronym for meteorological flows. And there the idea was that let's test the numerical prediction methods and forecast models, precisely the same numerical models that meteorologists use on a daily basis for weather forecasting. Let's test these methods and these particular models with the experiment. Because of course, if you have a bad weather forecast, you can always blame it on our incomplete understanding of, I don't know, cloud formation. So yeah, this weather forecast was off because the equations are not good, because these equations, of course, are full of empirical parameterizations, and everyone knows that. But so yeah, but the Navier-Stokes equations are pretty well known since the 18th century, and there is no so really the idea was here that okay, now if you can't model the real atmosphere, fine, but let's see whether you can predict the weather in this setup. And there were various groups running these simulations to model the flow in this baroclinic annulus. And it turned out that indeed, especially when it comes to things like subgrid scale parameterization techniques and stuff like that, it turned out that indeed they were systematically, for example, underestimating the propagation speed of the Rossby waves themselves. And based on what they learned from this so-called benchmarking with this experiment, now they are supposedly doing better weather forecasts. So this is one way where the lab models are still really can make a huge contribution even nowadays. So yeah, and this is some literature if you are interested in our works about these topics, including the Drake Passage or these polygon vortices on Saturn. But this is pretty much it for today, and thank you very much for your attention.